Now I wanted to explore this a little bit more. So you can see these x out 9 CV1, meaning the value coming out of here. So if I print the minimum and maximum of that, and the reason I did that is to better understand what is happening under the surface, I'm going to start padding, and given that we're going to do later the max pooling, meaning the maximum. So max pooling, what it is if you have, in this case, a 4x4 grid, and you're applying a 2x2 kernel with, in this case, padding of 0, the maximum out of this kernel will be the output. So in this case, 20, and then out of these we get 30, 112, and 37. So that is what we're going to do. We're going to get the maximum. So I want to make sure that whatever I'm padding is less than the minimum. So in this case, I put -1. So let me show you what I'm doing here. So if I focus on this tensor right here, and looking at the first channel, I look at the first 9x9 values for that tensor. I obtain this. Now, if I apply padding to that, a 2x2 padding, because as we know, that's what we're applying in the max pooling, the output of that will be 24x24. And if I show that, you can see that, for example, this 1.38, now it's here, and then the same with this one, because I've applied a 2x2. And now what I'm going to do here manually is for every 5x5 kernel, again, we're applying a 5x5 kernel, we're saying, okay, out of those 5x5, tell me what is the maximum number. So in this case, this 5x5 will be these first 5, as well as all the way up to here. So it will be this 5x5, it's hard to see, but it will be this 5x5. Disregard this to the right, is basically 5 on the rows and 5 on the columns. And then the maximum value of that, if I print this, will be 1.38, which corresponds to this value. And then if I do it for the next 5x5, will be this 5. And again, the highest value is still 1.38, and that's why we get that value. And then we'll continue with the next one. And again, 1.38 is still the largest. But then the next one, you're going to notice that is 0.68. So if we select the next 5x5, 1.38 is no longer there. And now we have these 6.8 times 10 to the power of -1, so 0.68, and that's what we obtain. And similar for the last 5 right here, 0.68. And then if we do that on the width dimension in a similar fashion, that will be the second one. And again, 1.38 still there, 1.38. The next one, 1.38 will still be there. Now in this one, you see 1.38 is no longer there in this 5x5. And instead, 0.93 is the largest, this one right here. And if we output the results of MP1, meaning right here, we should obtain the same values that we see here. Where this 9x9, applying this 5x5 kernel, we obtain these values which correspond to the values that we already knew here at the top. And you can see that the first, for the height, all of this corresponds to these ones. And for the width, again, this one is the top left, so it's applied for both the height and the width. And then the width, you can see that these values correspond to what we calculated here. Now we perform that operation on max pooling 1, again, the same padding that we saw earlier. Of course, the size is still 24x24 because we're applying 2 across each side of the height and width. So if we print that out with this padding, this is what we obtain for MP1. So if we, again, display the maximum of those values, notice that before we obtain 1.38 and then other different numbers, but in this second pooling, we obtain 1.38 for all of this small patch. So you can see that if we select the first 5, 1.38 is the greatest. And for example, if we select on the height, the last 5, 1.38 is still here. And then for the width, for example, the last 5 that we see here, you can see 1.38 still here. So when we print that out of MP2, meaning right here, those 5 by 5 values, we should obtain what we see here, 1.38, height and width. Now, if we do that one more time, and we show those results, now we obtain these, and then when we perform the max of these values, we obtain actually a different value here. And this corresponds to the width of this patch right here. And you can see that we have 2.02, and it's greater than all these other ones. And then the output is what we expected, 2.02. And of course, that value is also here. So that shows this as well. But again, you can see the height and the width. Now, you can see that it is somehow converging to some of the values. For example, you see 1.38 got converged a little bit, but here we introduce a higher number. So I was curious in knowing how many pooling layers would be necessary in order to converge to a value where if you do more max pooling layers, it will not change the values. So I performed this here, and it turns out that you would need 11 sequential pooling layers for all the values to converge. Of course, we're not doing 11 in our architecture, we're using 3, but you can see that some of the values will continue to change slightly and no changes will happen beyond this point. So I thought that was interesting. And just to show very quick that we get the same results as in VS Code, we could just run this. And again, here we'll just jump into a conf class. As you can see here, that will be CV1 and then come back. And now this X will be fed to this max pooling. As you can see here, and then that input will be to the max pooling again. And then here we'll perform the concatenation. And then here we're performing the last convolution. And then when I run this, we'll come back right here as we will have performed this SPPF module, as you can see here. And then we could step over that and visualize our features. And as shown previously, we're only displaying the first 32. So if we go here, these are the results of the first 32 feature maps coming out of the SPPF module.